For practical reason, SDR has to support incremental deployment and interoperate with the existing traditional router inside Tencent network. As this is different from the interoperating with the outside network. Okay, this is just for the Tencent inside network. And the traditional routers are running in MPLS network. How to efficiently interoperate with them is a big challenge for deploying SDR in the production network at the beginning. The straightforward approach is to implement the Intel MPLS functions on SDR servers. However, it's complex and not a good idea for future evolution, as we target to keep SDR simple and clean, and we don't want to introduce additional features which will be deprecated later. So finally, we choose to deploy a commodity MPLS switch between SDR and the MPLS network. This MPLS switch acts as a PE to communicate with the traditional router using MPLS technology and communicate with SDR with only IP technology. BGP session is established between SDR and MPLS switch for routing information exchange. What we have done is just a minor change in the SDR software. After that, SDR can interoperate with the existing MPLS work properly. And the whole MPLS network is transparent to our SDR. This approach greatly speeds up the process of deploying SDR in our production network. Next, I'm going to talk about the scalability of SDR. For SDR interconnection network, we leverage classic cloud architecture, which has been broadly deployed and fully verified in our data center network. And BGP is deployed among servers, access switches, and core switches. Each server is double connected to access switches. Data plan, control plan, and the routing plan has implemented its own scalability mechanisms respectively. With this design, each layer of the network is able to scale up horizontally. Even more, underlay network and overlay network can be operated by different teams accordingly. So currently, SDR provides 3.2 terabits per second forwarding capacity and 100 K per second routes update capacity. And the capacity can be scaled up easily by adding more instances into the cluster. Okay, the hardware acceleration. To further improve the forwarding capacity, we have also introduced the programmable switch, Tencent Smart Switch for hardware acceleration. In order to cooperate with the Tencent Smart Switch for offloading, here data plan employs an efficient offloading framework for real-time detecting and reporting the elephant flows to the control plan. The control plan then programs Tencent Smart Switch with the flow information. Apart from that, the control plan is also responsible for collecting specific flow informations related to high volume traffic, mainly from our external management system, and synchronizing them into Tencent Smart Switch for offloading purpose. So after that, for the traffic, match the flow rules on Tencent Smart Switch is forwarded directly. For the remaining traffic or signaling packet like BGP BFD or IP fragments, it will be redirected to the server-based data plan for normal packet for processing. Tencent Smart Switch provides us hardware level high performance with general forwarding pipeline, which have greatly improve the SDR forwarding capacity and meanwhile maintain a high flexibility. Reliability. Reliability is another critical piece of capability we had to provide for our customer. First, according to the redundancy architecture design, we know that any single point failure, no matter it's a server, a link, or switch, will not affect the whole system availability. Second, if the entire control systems fails, data plan is able to continue to process packet accordingly as it keeps the last good state of forwarding table. If the entire routing system fails, the control plan is also responsible for real-time monitoring the health of the routing plan. Control plan will stop synchronizing the forwarding routes from routing plan to data plan. Thus, data plan can still forward packet properly. Apart from that, normally we deploy the 2 routing instances at each site for routing plan redundancy purpose. For scenarios which only 1 BGP session is allowed, we had to use another mechanism. Specifically, we split BGP functions into BGP speaker unit and the BGP root computation unit, and then distribute them among servers at the granularity peer, which allow us to limit the failover scope, restart a single instance, and recover the BGP session quickly. We also have implemented a couple of probing and fast failover mechanism to improve the reliability of SDR. By leveraging these technologies, we are able to provide non-stop forwarding and non-stop routing capabilities for our customers. For operationality, we have built a real-time monitoring and operating system, RMOS, on the bottom of this diagram, covering all aspects of the SDR system. Here we just take the data plan monitoring as an example to illustrate the mechanism. First, 3-level data plan probing, which are cluster level, server level, and the core level probing in order to quickly detect and handle failures. Second, we have conducted a critical resource monitoring for resources like buffer queues inside the data plan. Once any anomaly detected, related servers will be isolated soon. And in addition, sufficient statistics and events like packet drops, CRC errors will be reported to control plan in real time. When it exceeds a certain threshold, the device will be removed from the cluster. And the RMOS system is still